Assalamualaikum everyone. So in this video, we're going to talk about two-source interference. We will discuss double slit experiment and we will try to do some past paper question as well. So starting with the conditions for the interference fringes in double slit experiment, the light should be coherent. This is the first condition. It's mean the light should be in phase of the two sources, and the light should be monochromatic. It should have a single wavelength. Okay, so this is the experimental setup shown in diagram, and this is S1 and S2 are the two sources, and this is the screen on which we can observe the fringes. Okay, what we do usually, we use a single source here, and from that single source, light is coming towards these two slits and it will pass through it. So these two slits are actually acting like a source. And as the light is coming from the same source, so it will have the same frequency, so we don't have to worry about that both the sources will of the same frequency or they are not. And secondly, this source is placed at an equal distance from S1 and S2, so they will also be in phase. So by using this method, that we are using a single source and that single source is placed behind the double slits, so these two slits are acting like a source. We met both the condition that the light is coherent and the light is monochromatic as well. Okay, so when the light is going on the screen, where it will, when crust meets the crust, there will be a constructive interference, and the condition is this: the path difference should be n lambda. And when there is a crust is on the trough, there will be a destructive interference. This is the condition for that thing. Okay, so this is how you can see this thing. So you will see maxima at the center, and the central maxima is the zeroth order maxima, and one above or one below maximas are the first, and the two above or the two below are the second maximas. Okay, and in between each maxima there is a minimas. Okay. Okay, so why there is a path difference, how this thing is occurring basically, if you see the light coming from S1 is traveling that much distance, and the light going from S2 is traveling that much distance. So basically this S2, if you observe, it's approximately covering this much distance extra. So this is basically the path difference that matters. If that path difference is multiple of lambda, then this will give you constructive interference. And if it gives you half integral multiple of lambda, it will give you destructive interference, as we have seen above. So this experiment is commonly called as Young double slit experiment. This is the experimental setup in which we have used a single source here, and we have placed a single slit here. This slit is just placed to give direction to the wavefronts. Okay, so wavefronts are going in that direction, and here we have placed two secondary two slits, and when this light pass through them, these two slits are acting like two different sources of light, and the waves will meet at a point where they are constructively meeting, there will be a maxima, and where they are meeting destructively, there will be a minima, and this is how you can see it. Okay, so this is the diagram. You can relate this thing by this diagram. So this is a slit A and B. The separation between A and B is called A. Okay, the distance between the A and B is called A, and the height of the fringe from the central maxima is called X. Okay, and this is the screen. The separation between the screen and the slits, it's D, and this D is the maximum distance among all three of them. Okay, this will be of the higher magnitude. They are usually measured in centimeters or millimeters. Okay, so, and this is the relation for the Young double slit experiment, that lambda is equals to ax divided by d, and you know what the ax and what d are representing. Okay, so okay, let's move forward. So in this experiment, what matters is how much far the fringes are. Let's suppose if you see the fringes like this is the central maxima, how much height the first maxima will have. Okay, it can be changed by different parameters. Let's suppose if you change the wavelength, the height of the maximas can change. Okay, it can be like this, that first maxima is here, second maxima can be here, and third maxima can be above. It depends on different factors, and here they are mentioned. This x is the height of the fringe from the central maxima. It directly proportional to the wavelength. If you increase the wavelength, the separation between the maximas will increase. It's directly proportional with the D. D is the separation between the screen and the slits, and is inversely proportional with the A. A is the separation between the two slits, okay? The gap between the two slits, you can say. Okay, let's try to solve some questions. Question is from May-June 2025 paper. Question 31. Okay, so light of single frequency from two coherent sources interfere. This is from 2025. Okay, coherent sources interfere to produce a pattern of the dark fringe on the screen, which change result in larger fringe separation. Okay, so what the fringe separation was, X is the fringe separation, right? X is fringe separation, and what we need a larger fringe separation. So we have to go back to the relation that we have just did. Lambda is equals to a x over d. So I can rearrange this thing for the x. So x can be written as lambda d over a. Okay, so we know x is directly proportional to lambda, x is directly proportional to, sorry, this is lambda to d, and x is inversely proportional to a. Now let's see the option increasing the distance between the two, between the source and the screen. If you increase the d, this the fringe separation will increase. It seems correct. Okay, in B, what the increasing the distance between the two sources. Increasing the distance between the two sources, he is talking about A. If you increase A, the X will decrease, so that is not a right option. Okay, same goes for these two. You are decreasing wavelength in C and D, so decreasing wavelength will decrease the X, not increase the X. Okay, and the next question, this is also from 2025. Light of single frequency, single wavelength is incident normally on a double slit, and again interference fringes are observed, but we have the distance from the double slit to the screen is given, that is 0.6, and the fringe separation is 1.8 that we have. Okay, so here you have D, here you have X. The distance from the slit to the screen is increased by 0.9. So this is increased by 0.9. What you have to find, what is the new fringe separation. Okay, you have to find fringe separation here. So the basic relation is lambda is equals to ax over d. Okay, and as we know, x is directly proportional with d. Okay, so we can use the ratio proportion method as well. Let's suppose when x was 1.8, there is a x and there is a d. The d was 0.6. Now x is increased by d is increased by 0.9. So 0.6 was already, 0.9 is increased. So what will be the x now, the new x? Okay, so this thing is basically 1.5. So we can use the ratio method. It can be written as 1.8 divided by x is equals to 0.6 divided by 1.5. So this thing will give you x is equals to 1.8 into 1.5 divided by 0.6. Doing the maths, it will give you 4.5 millimeter. Okay. Okay, if you notice one thing, I haven't changed the units of this x. Okay, because I need the answer in millimeters, so I'm not converting it. Okay, so that is the reason why I'm getting the x in millimeter. Let's move forward to the next part. Next question. This is also from 2025 paper. Red light of single wavelength from a laser is incident on a double slit. A pattern of interference fringes observed. Which change increases the separation of the interference fringes on the screen? It's the more or less same question. You have to increase the x. We know lambda is equals to ax over d, so x is lambda d over a. Now you can see the options. Decreasing the distance from the double slit. If your distance is basically the d, they are talking about d. If you decrease the d, what will happen? The x will also decrease. Okay, so it's not the right option. Decreasing the separation, they are talking about a. So if you decrease the separation, the x will increase. Yes, this is right. Okay. Okay, let's move to the next question. This is the last question of this worksheet, and this is from paper 20 year 2024. Interference fringes of separation x are observed on a screen at a distance given. So what we have d from a double slit that is illuminated by a yellow light of wavelength this. At which distance from the double slit? So you have to find distance, slit interference, the same separation, the x should be same as it was before when using a blue light. Okay, when using a blue light. Okay, so we have two things. We have yellow light case and we have blue light scenario. Okay, so relation is same. We have lambda is equals to ax over d. So when you rearrange this, x is equals to lambda d over a. Now putting the values, lambda we have 600 nanometers. Okay, you can convert it or you can simply write it down 600 nanometer. It does not matter at the end. And d we have 1.00. And what the a is, it's not given. Okay, again you have to find. Okay, for the second case, you can same write x is equals to lambda d over a. When you put the values, x will be, the wavelength is 400 nanometers minus 9. Okay, into d is unknown. In that case we have to find it, and there is a. Okay, we don't know about a as well. Okay, a is also same. Acha, what we can do, we can equate these to the left hand sides because x is same for both the cases. It's given in the question. So you can say 600 into 10 power minus 9 into 1.00 over a is equals to 400 into 10 point into d divided by a. So what we can do, this a will be cancelled out with this a. This 10 power minus 9 cancel out with this thing. So this d can be written as 600 and this 400 will be divided on the left hand side. These zeros cancel. D is 6 by 4. That will give you 1.5 meters. Okay, so answer is D. Okay, that's all in this video. See you for the next.